well, no, let's go here. So let's just recap what we're talking about for the last little while before we move on. You'll recall that what we've talked about are the fact that we'd like to do conservation on three important quantities for this class. One is conservation of mass, which is really volume in, volume out minus volume in equals net accumulation. And there are two others which we still have to do. The second is conservation of momentum. We've said that Newton's second law is F equals ma. Mass times acceleration. Acceleration is the rate of change of velocity. So the ma term is really a rate of change of momentum has to equal the forces applied to a body. And so that's been implicit in what we've done with Bernoulli. So from our Jetlev calculations to the cars being blown off the runway at San Francisco International, that all relies on conservation of momentum. We've solved those problems using Bernoulli's law, but a slightly fancier way of doing it is to use Reynolds transport theorem. And finally, we will do conservation of energy. And conservation of energy also ends up as the Bernoulli equation, but with extra terms to represent the fact that we can add things like energy into the system by a pump, and we can also calculate energy delivered by the system for energy machines like windmills or hydroelectric plants. And we can also use it to calculate for non-ideal viscous flows, not inviscid flows, which really Bernoulli deals with. And so those are the three things we do. Conservation of mass we've done. Conservation of momentum we'll do this week. Conservation of energy we'll do next week. And that's the plan. We use Reynolds transport theorem. You'll remember that the basic tenets of it came out in two forms. And we wrote those two forms, if you recall, as something like just this expression here. We wrote these forms as something like density times the rate of change of volume with time plus a constant volume multiplied by a rate of change of density with time plus a mass, rate of change of mass has to sum to 0. And the other component that we had to deal with is that in looking at this mass rate, it was positive out, our sign convention, negative if it's in. That was very important. And in addition to that, we also had to accommodate for the fact that the velocity to a static observer is equal to the velocity of the control volume plus the velocity of the flow relative to that. And so in our example, if you like, the water flowing out of the fire hose is a velocity w. It's a vector. The velocity of the boat is the velocity of the control volume. And the velocity of someone standing on the quayside watching this is, so the observed velocity of this whole system relative to that is the velocity relative to this static reference frame. So not the velocity of this person, but the velocity which he views things. So in other words, if the boat is flying water at 1 meter per second, if the control volume is moving at 2 meters a second, then the static observer sees this at 3 meters a second, just from somewhere. So that was the basic tenet. So I guess the two important expressions are, we have this mass conservation equation, which is the first thing we wrote just then. Increases in volumes are positive. So if the volume gets larger, and also increases in density is positive. So those are our sign conventions. And so we derived it using Reynolds transport theorem, but perhaps that's an overly officious or rigorous way to do it. If we just account for things in some reasonable way, we can end up doing that. In fact, we didn't really, when we did the examples last time, we really just used this single expression. So this is worthwhile, obviously, knowing. And so also, I guess, in terms of perspective, the second exam is typically, we'll cover stuff from Bernoulli equation, conservation of mass and conservation of momentum. And so typically you'd expect a conservation of mass question to be on there somewhere. So, not to spoil our nice conversation here today with such thoughts of that, but that typically would turn up. Okay? Bless you. So that's the first of our conservation equations that we've dealt with, conservation of mass. So what we'd like to talk today is the next one. And the next one is for us to be able to deal with conservation of linear momentum. Of course, momentum is this quantity, mass times velocity. Velocity is a vector rather than a scalar, has both direction and magnitude. And you will recall that what we'd like to be able to do is to be able to substitute the fact that this extensive quantity, B, is equal to mass times velocity. And by definition, in Reynolds transport theorem, which is quite an amazing expression really, quite general, it allows us to be able to conserve both mass, momentum, and energy. So it's kind of quite clever in the way it works. Is that this intensive quantity B is just this extensive quantity divided by per unit mass, which by definition is this, which is therefore just velocity. And so if we go ahead and substitute this into this, we end up with those magnitudes of velocity, which is a vector, and a velocity here, which is a vector. And on this right-hand side, this term here is going to be mass times velocity. And so this left-hand expression is just, if we write it out in full, it's just this component here. And if you look at this and think about what it is, if we write it a slightly different way, I guess if we wrote it as mass times, if we thought that the mass wasn't going to change, then this might look something slightly more familiar to you, right? This, by definition, is acceleration. And so this, actually, by definition, is sum of forces. And so that's actually everything we need to do for Reynolds transport theorem to get it to work for conservation of momentum. And it's really just a substitution of a new quantity. This extensive quantity of momentum goes into here, and we end up with a new expression. But we shouldn't be wary of this. We should just realize that with the substitution of this new term, we end up with a new expression which says that as we sum forces, the sum of forces applied to a system have to be relative to, this is a rate of change of momentum due to our convective accelerations. And this is, if you like, a momentum flux. And so basically what it says is that if you're standing on the elevator and conserving momentum, the forces that are applied to some kind of system have to be due to two effects. One is the fact that some momentum might be coming into the system. Maybe some water is coming in at very high speed or high density, and therefore it's coming into the system across the control surface, and that amount is changing with time. Or there may be some amount that's leaving the system across the control surface. So this is the amount that goes across the control surface, and this is the accumulation of momentum in the system. So it's exactly the same as conservation of mass. It's kind of a messy diagram, but let's not worry about the derivation so much. Let's worry about trying to solve some problems using that. We didn't look at any videos yet, so let's go back and mess around with that briefly, see what we have, to see what kind of applications this might be. Hopefully these will come up. So a Pelton wheel is one way of being able to convert kinetic energy into rotational energy. So this is on the left-hand side, you just see an air jet being applied onto this Pelton wheel. I guess we didn't see the beginning, so all the Pelton wheel is a bunch of cups which are arranged this way. You fire a jet of typically water onto them, air in this particular case, and it pushes it around. The next one comes available. And so if you imagine putting a whole bunch of teacups around one of these wheels, it's one way to be able to turn a linear flow, which you might have a jet of water coming out of a dam, into a rotational flow. Rotational rotational acceleration is useful for us because it can obviously drive the shaft of a generator, for example. And so that's one reason for doing it. What else? Well, we've done this. You've seen this many times.
And power plant on the ground, or more appropriately on the water. That's it there, floating.
And so the Jetlev is exactly the same idea. We actually solved this problem, as I recall, using Bernoulli's equation. And so now what Reynolds transport theorem allows us to do is perhaps do it a bit more elegantly to be able to solve the same problem and be able to figure out, for example, what the velocity has to be that comes out of the base of this for the jet that is able to pick up a person, the weight of a person off the ground, and therefore from that you could, for instance, dimension the pump that you might want to apply if you are designing such a frivolous piece of equipment, kind of a cool piece of equipment. I didn't look at this. So look at this. I hope this isn't over printing. Oh, this actually, we could put the sound on this, then I'll stop talking.
Legends of their destructive potential have been around for 99.
It's not getting sound on this.
But could a ruptured tank really burrow through a brick wall? Into the next county.
Here we go, shearing the regulator off the tank. Attempt number 2. In 5, 4, cross your fingers, 3, 2, 1. Yeah! That's the sound!
So they guillotined the end of a gas cylinder in the lab. This is why when you move gas cylinders, you put this protective collar around it as you move around. It falls over and knocks the top off by accident, then it's sometimes a problem, as you might see here.
Did it have enough thrust to crack the wall?
The so-called sleeping giant and all these safety admonitions for labs of not to move gas cylinders without properly putting this collar on the top, secure them in place so they don't fall over relative to the bench, and because this is what happens with them. They can fly across the lab, they can go through block walls, and be quite destructive. And so quite an interesting illustration of basically power. So you're taking potential energy, P over gamma in the Bernoulli equation, and you're changing it into V squared over 2G. And then ultimately you're trying to destroy that momentum by having it hit the wall and stop, taking that velocity times the mass of the cylinder and stopping it. That would be the force that would be applied to stop it. So amazing destructive power in relatively innocuous item contained in many labs. Okay, this is it. So what else we got? Oh yeah, so.
Hold on. This is map gas bottle rocket.
Good?
Do it.
So,
it makes a shitload of noise.
So good use of a propane torch, I guess. So anyway, or at least one use. I'm not sure it's a good use. I probably shouldn't say that. Yeah. So and also we can use it for kind of fluid mechanics things as well. Things that we've talked about and solved using Bernoulli, the so-called undershot weir. The idea that you can change the elevation of this, the penetration, if you like, of this weir, and from measuring the upstream and downstream elevation change, you can use that to say something about the flow rates in these systems. I guess I was probably talking over the noise for that, so perhaps you won't get that on the recording. Does it not do it? I thought this was interesting. Maybe it won't do it. I thought this is an interesting article in Science. Yeah, okay. So there's one question here. or one figure that I was looking for. Which is it? It was basically making the case that Pumas, of course, which the Nittany Lion, I guess, is a version of. Maybe this is the figure. Body mass, I think that was it. Maybe this is it. Yeah, this is it. Okay. So I thought interesting. So they're talking about when puma kill animals, that they choose how much energy they put into their pounce depending on the size of the animal. And so if you look at this figure here, it's the mass of the prey that they're preying on. I don't know what is 5 kilograms versus 100 kilograms. 100 kilograms, I guess, is person size. And the expended energy in the pounce in terms of kilojoules. And so this is also some measure of choosing the amount of energy you want to put into the system to be able to do, I suppose in their case, the amount of damage they want to do to be able to make their prey immobile, and so by striking. And so no different in some respects from the things that we're trying to do in terms of understanding balances of momentum. You leap, you have a certain velocity as you leap through the ground, or the puma does, has a mass, and therefore when it strikes something, it's the destruction of that momentum, mass times velocity, that is the force that the prey ultimately feels and ultimately succumbs to. And then we'll do an example like this, but the idea of this is the idea of a monitor, so-called monitor, M-O-N-I-T-O-R. See this kink in the tubing as it goes in here? Maybe if it comes back, you'll see this kind of roundabout shape in the monitor. So these are used for alluvial mining. This is, of course, the San Francisco 49ers, the 1849 gold rush in the Sierras of California, where the mining was not so much underground gold mining, but actually placer mining, where you just wash away the riverbanks with a monitor. You get the slurry, you put it through a sluice, you take out the heaviest density components, which of course would be the flecks of gold somehow, and you'd be able to use it. So there's a huge amount of damage done in terms of this method of being able to remove alluvium from these systems. And of course, Grass Valley up in the Sierras, about 3 hours east of San Francisco, is the place where they just recently had all these, this so-called, I can't remember exactly what the name of the fire was now, but they had a uncontrolled forest fire going that was tough to be able to put out. So all of these involve using something to do with conservation of momentum. And so that's what we'll attempt to do. Okay, so I guess back to the real McCoy now, and talking about this. We won't go through this. We've kind of done this. So what we've done already then is we've made some comment that we can use in Reynolds transport theorem this extensive property and this intensive property to substitute into this. And as a result of that, what comes out of it is, from our generalized expression, the fact that the sum of forces have to equal a rate of change of momentum within the volume plus the amount of momentum that goes into or out of that volume across the control surface. So in a philosophical way, it's really no different from talking about conservation of momentum. It's just, or sorry, of mass. It's very easy for us to understand what mass is. 10 people go in, 9 people go out. You net accumulate 1 person per unit time. And so it's the same thing here. 10 units of momentum go in, 9 units come out, 1 unit of momentum accumulates, and because of that accumulation, that more goes in than comes out, you have to apply a force to keep that thing in place because it wants to move. And so that's kind of the canned description, if you like, of physically what's going on, if you deal better in those kinds of descriptions. So always think of these as just a balance of momentum. This is the amount going into or out of the control volume. If more goes in than goes out, some net accumulates. If some net accumulates, then you have to apply a force to be able to hold that body in place, hold that monitor in place. Clearly, when you're squirting fluid out of that, you have to hold it in place, presumably because more momentum is going into the system than is coming out of it, and therefore we have to anchor it. In most of the systems that we'll deal with, this term will typically be 0. And so we don't talk about accumulation. We'll talk about steady state systems. And therefore, the expression becomes slightly simpler. Okay. If we write out this full expression, I guess we also have to remember that this extensive quantity of momentum has a vector in it. So, in other words, as you can imagine, when you're resolving forces, forces have x, y, and z components, and also the velocities have x, y, and z components. Just in the same way as when we write F equals ma, which is really what we're writing, both of these terms have components. And so when we write this out, the full expression will look a little bit like this. Typically, we won't worry about this term. We'll look at steady state systems, I think, in this class, so we don't care so much about that. But it's just to reinforce the fact that this quantity is a vector, and it has 3 components. As opposed to this velocity, which is really, in words, the normal to the boundary velocity. And of course, actually, if you remember, the slightly nicer way that we've thought about writing this is that this term here, density times normal to the boundary velocity times the area. So this term here, if I'm not going to mess this up too much, is what we would refer to as volumetric flow rate, Q. And this amount here, the density times the volumetric flow rate, is just equal to what we've called before as mass flow rate. So this is a scalar. It has magnitude but not direction. It's either into or out of a system, positive or minus, positive out, negative in. Maybe it seems backwards. So this is a scalar quantity, but it's multiplied through by a velocity. And so it's perhaps not surprising that this term here is basically this mass flow rate. And so multiply mass flow rate by the velocity in the x direction gives you one equation. So this would be by resolving in the x direction. If we were resolved in the y direction, it would be these components. And these would be the appropriate, this would be the same mass flow rate across the surface. So this wouldn't change. This would be the same amount that would be applied to each of these values. And so that's the one important difference, I guess, in dealing with mass, momentum transfer rather than mass transfer, is that we have to lodge in our minds the fact that this is a vectoral quantity and operates on a scalar. Okay, so that's how we can think about it. So that's our way of thinking about it. In the same way that we had a sign convention when we dealt with problems of or the conditions of mass transfer, we also have a sign convention we have to deal with here. The sign convention is going to be exactly the same, and if it's outflow, it's positive, and if it's inflow, it's negative. So we won't change our sign convention. We've used a uniform right-handed coordinate system in our system. Hasn't really mattered so much in many of the things we've done. We've universally chosen this convention, sign convention of z upwards, and we've universally considered this sign convention of positive for outflows and negative for inflows for the reasons we talked about last time, the directions of the normal. And so we'll also have a sign convention when we talk about momentum. And so we said before that when we deal with this, we're basically going to ignore rates of change terms in time. And so we can just use this equation on the right-hand side. And so what we see is that there's a mass flow rate here, which is multiplied through by a velocity. And so the sign convention that we'll use is the mass flow rate is exactly the same as before. We've kind of said that. Don't repeat it. So that's true for this. But this is always our Cartesian coordinate system. After René Descartes, of course, which is our positive velocities in the x direction are in the x direction. Positive velocities in the y direction are in the direction of the y direction. And so if I do that, then I guess the final one would be back towards me, which would be in the z direction. It doesn't particularly matter so much about the right-handedness for anything we'll do, but it does matter that the positive directions have to be in the direction of the positive coordinate system, which also means that forces in these directions will be positive in these directions too. So that's what we have to remember. And so you see in this that the magnitudes of these Cartesian velocities operate on the scalar. And so we just have to be able to apply that and make sense in what we're trying to do. So this expression here is what we're going to look at now on the next little page, to be able to look at the sign convention. And this is perhaps the one takeaway thing that you should go away from here with today. What's this? So this is this expression. You'll see that this expression on the side here is just this. It's perhaps easier to rewrite this as instead of, if we take the, okay, that's it. So we don't care about the density. Obviously density times velocity is now velocity squared term. And we said before that we could, the reason it looks like this, I suppose, is because of what? It's because we can write rate of change of velocity with time as rate of change of velocity in space. And so this becomes velocity in the x direction. So the fact that we end up with a change in velocity in space times velocity is kind of manifest in this expression here. This is really, because if you recall, this is just equal to density times this is just sum of forces. Actually not density, this would be mass. Mass times acceleration is equal to sum of forces. Making a bit of a hash of this, but trying to make the point that the reason that we have you'd expect momentum to be mass times velocity, but apparently we have two velocities in here with this velocity squared term. The reason is the same as in Bernoulli, we have v squared over 2g. That comes from a rate of change of velocity with time, and equating that to Newton's second law. So this acceleration here is what looks like this, and it looks like these two components. So velocity times a velocity, and we can also write this as a half rate of change of velocity squared, if you recall. So it doesn't matter. So let's get back to our sign convention. So this is our body. We'll choose flows in the x direction, so we have some velocity going in the x direction. So for our sign convention, if we look at this, if the flow velocity is in this direction, then the normal to the boundary velocity, remember we have a unit normal coming out like this. And so for our sign convention, this term here would be positive or negative. Right? It's going into the body, so this would be negative on this side. Sorry. Jeez. This would be negative, right? So this term here is into the system, so the term which is normal to the boundary, the green term, has to be negative. This is going in the positive direction of the x direction, so this term is positive. And so positive times a negative gives a net negative. So the scalar value of velocity across this surface has to be minus v, whatever the size of v is. So v is the size of it, and it's going to be negative. When it comes out the other side, the velocity is still in the same direction. This term here is out of the system, It's directly aligned with the unit normal. And so this term here, by definition, has to be positive. And so this is positive. The magnitude of the blue vector, which is just the v term, is in the direction of the coordinate system, x, positive x. And so this term is also positive. And so when you have two quantities both positive, then the resulting quantity is positive as well. When you have one quantity that's positive, one quantity negative, the resulting component is negative. But the magnitude, if you do that, then the magnitudes of these velocities, you don't have to care about it being a vectoral quantity. It can just be the scalar magnitude of those. So that is really what you have to get into your head about the sign convention. The sign convention has to be that the velocities in the x and the forces in x have to be aligned positively in the direction of the coordinate system, but the into or out of across the boundary magnitudes still retain the positive outwards and negative inflow conditions, right? So let's take the same example and just reverse it. So now you have the flow in this direction. So the flow of v is in this direction. So v is negative 5 meters a second or whatever. You can choose whatever number. So the scalar value of this is -5. So what happens now? This is the green one. This is the normal to the boundary. And so this is out. It's aligned to the outward one. This is the velocity here. And so this term here is going to be what? Has to be positive. It's going out of the system. Our convention is out. But the direction of this is in the negative x direction. So this is negative. And so a negative times a positive is a negative. So if you take the scalar value of whatever the velocities are and squared it, then you'd have to apply a minus sign to that to get the right component. Okay. On the other side, again, doing the same. Normal to the boundary velocity, this is the normal. This is in the opposite direction of the normal. Therefore, the dot product of this is negative because it's inwards flow, right? Inflow, I suppose. And again, the magnitude, the velocity, direction of the true velocity v is also negative. And so a negative times a negative gives you a positive. So maybe the most important thing that we've talked about today is kind of embodied in this particular figure. So you've got to do your counting correct. It gets a bit complicated, but that's basically it. So remember the ways of being able to do that accounting. Yes, sir. Which one, sorry? This one here? This? Oh, the normal vector. No, so yeah, the n is just a vector. So the way that we do our counting across this boundary is just by defining a vector which has a unit length and happens to be arranged so it's directly normal to the surface. And so this is, if you want to think about the dot product is just the dot product, the vector product, vector sum I guess it is, of the velocity vector and this normal to the boundary vector. If you just account for this as positive outwards and negative inwards, then you don't have to worry about this n. Okay. Yes?
Does that say like plus or minus v, or is that
This is you mean all of this notation of mine plus VE? Just positive. Yeah, sorry. Yeah. Positive is positive. Sorry, yeah. This is just my shorthand for positive and negative. So everywhere you've seen that. So this one's negative, positive, positive, positive. Okay. So this is an important figure. I think this is the key to a lot of the stuff we're doing is if you understand this figure and can implement it, then all will be maybe well. Okay. Didn't get quite as far as I thought, but fine. We'll go as far. So let's apply this thing to. We do this. Let's stop. So finally, actually, let's skip beyond that example and just put this. So this is finally the expression that you might want to use. Looks a bit more simple than everything else. We've written this before. We've called this uppercase m dot, right? But it's the same thing. And it's just saying that flow velocity across a surface multiplied by the mass rate of flow across that surface has to equal the sum of forces resolved in that direction. You can do it in x, you can do it in y, and you can do it in z, but regardless, you'll only do it one at a time. And so you only really need one at a time. In the stuff that we'll do, I can't imagine we'll do anything that will have a time component in it, so we don't care about that. And so really what we're just doing is this portion of the expression here, which is, so if I write that out so it's not quite so unclear, this is flow velocity in the x direction. This is what we've called mass flow rate, has to equal the sum of forces in x. So that's just a... And so maybe guided by the previous figure that we looked at and helped by the words said here, is that mass flow rates are always positive if they're outflow. Mass flow rates are always negative if they're inflow. And importantly, this velocity that we pre-multiply mass flow rates by is always positive in the direction of the coordinates, as we've done. So before we had an x coordinate, so forces in the x direction were positive in this direction, velocities in the x direction were positive in this direction as well. And likewise for y. And so the reasons for that are by the dot product. I don't think you need to know that. You should know that from your previous math and calculus classes, but you don't need to know that here. But you need to be able to use this expression here. Okay. All right. So what will we do? Won't do that. We'll do a simple. We'll go back to the simpler one. Okay. So we've done this question already. So I guess the basic question is, if you have an undershot weir and you choose to put this gate here, how much force do you have to apply to this gate, the so-called reaction in the x direction, to hold it in place? So at some stage where the gate is all the way down, the reaction you can calculate just from your understanding of statics. From the third week of this class, we talked about fluid statics and pressures on structures. If you take the weir gate up, then all of a sudden you get flow coming out of here, and the question is, does the force that you have to apply to keep this gate in place become less or more? You can think yourself as to what you think that should be. Should it become less or more? So how do we do the comparison? Well, with the gate closed, the free body diagram we have looks like this. We have the weight of water acting downwards. We don't care what that is. We have a reaction force acting here, and that has to equal the amount of fluid on the upstream side, which would be this resultant force here. You can probably remember that the resultant should equal what? It should equal an area multiplied by a unit weight times the depth of the centroid. If this thing is of height h, which I think it is, and of length, I don't know, length 1, so of length 1 into here, so this is 1, then the area is just going to be h times 1. The unit weight is the unit weight of water, and the depth of the centroid is just going to be h over 2. Not where it acts, but the magnitude is it. So it's going to be equal to a half uppercase h squared times unit weight times b. Okay. B is the magnitude into the board. So this is not 1, this is b. And so that's the magnitude of this reaction, which is going to be the same as equal to Rx, because those are the only two forces acting. You have this force acting on the upstream side, this on the gate, and so this has to be the reaction. And so if you do that, you end up with this expression here, which is in the bottom. This example, of course, is out of your book. It's equation 2. Okay? So that's the first one. That's what we know how to do. So what we'd now like to do is to do the calculation for this where we open up the sluice. And so when we open up the sluice, there are two things that change. One is that we now have water in the upstream side going at some velocity. And we could imagine that this is just moving at velocity u1. And also downstream of the sluice, the water is coming out at some velocity u2. And so now we can do the same balance using our expression. And so what we're going to do now is we're going to try and calculate the velocities times the mass flow rates are equal to the sum of the forces in the x direction. So this will be velocity in the x direction, not a vector. I didn't mean to underline it. This will be magnitude of appropriate magnitude of velocity, positive in the coordinate direction, negative in the negative coordinate direction. This is mass flow rate in or out, positive outwards, negative inwards, and this is forces. And so if we apply that, then we end up with this expression here. And let me just see exactly what I was trying to do. Yeah, so the forces we have are a force acting upstream, a pressure force acting downstream, and a pressure force acting upstream, plus these two velocities. So perhaps I should have done it by hand so you could keep up with the pace of this. And so if we do those calculations, I guess I can make this smaller. So maybe it does fit on the page at the same time. So what do we have acting upstream? We have this force, which let's call F1. Which we've just defined here, right? We did this calculation for FR, and force F1 is just exactly that. It's a half unit weight, the upstream depth squared multiplied by the width of the weir. We're holding it in place with a reaction. The reaction for our coordinate system acts in the negative x direction. So this is minus Rx. If we look at this portion here, we have a force which is acting upstream, which we'll call F2, by cutting off this flow here. And we can calculate the depth of that as being equal to unit weight times the height of the downstream depth, the depth squared times b. It's exactly the same as this, but just the depth has changed. It's the same triangular distribution. The force is acting upstream, and therefore in our coordinate system here it is negative. So that's this term. And we have some force that's acting on the bottom, which again is in the minus x direction. So those are the forces that are acting. And so those have to be equated, if you like, to magnitudes of the momentum change. This term on the left-hand side is just the velocity multiplied by the mass rate of change of flow. This term here is just that. And what are those terms? Well, actually, we can write it out here. The upstream one is going to be U1 multiplied by U1 times the area, which is height h multiplied by b. Right? So this multiplied by unit weight. So this term here is m dot 1, which is the amount of fluid going across this surface here, or the momentum of it. So the velocity is positive. These all are positive. This is positive. The flow is going into the control volume, and so this has to be, in my shorthand, this is negative. So this is going to have a minus sign attached to it. The stuff coming out from the downstream portion is going to be exactly the same, but it's going to be equal to U2 multiplied by U1 lowercase h times b. This is the area, this is the unit weight, and this is the velocity. And so this term here is the mass flow rate across that surface. Sorry, forget what I said. This is positive, right? Because it's in the positive direction. This term here has to be negative because it's net flowing into the control volume. Still ends up being overall negative. In this case, the downstream fluid flow is positive out of the system. It's the same as this one, actually. So this is positive. This is flowing out of the system, so this term is also positive. And so if we take these two terms and we substitute in here, then we have a force balance because of all the other components on the right hand side. We have the momentum balance because of momentum going into the control volume and momentum flowing out of the control volume, which are these two components here. And if you put those two together, this is just a fancier way of doing this. We said that this is positive and this is positive, so this term here is net positive. We said that this is positive and this is negative, so this term here is net negative because of this term. And then when you put these together, you end up with substituting these components into here. The punchline, if you want, I realize we've gone a bit over, is that now if you resolve for the reaction that you have to apply on the gate, then you have to apply these forces. This is the upstream force pushing on the gate. Before, when the gate was closed, this was the only force we had. Everything else was zero. Now, when you open the gate, you get a reduction in that force due to the fact that momentum is flowing out of the bottom part of the gate, which is this term. It's less than this term, so it's subtract from it. We don't care about this. We subtract also the outflow from the downstream part, the inflow from the upstream part, and oh yeah, this is the upstream part. So this is the upstream. So now what's going on is that you're subtracting off the pressure below the weir. You're subtracting off the fact that momentum is going out of the bottom of the weir, and the fact that there's also this additional amount of momentum coming into the top. And this amount here has to actually, was the only component that adds to it. So the bottom line is that when you open the gate, kind of what you'd expect, to close the gate, you're holding all of this water upstream with this force. If you pull the gate up, then you expect the force you have to apply would be somewhat less, because you're actually allowing fluid to come through the system. So that's an exposition, if you like, of how to use this. So I apologize for going over, but remember from this, you just have to do the appropriate accounting for sign convention. Okay, thank you.